One thing we happen to know is that if we have a symmetric or a bell-shaped graph, that 95% of the data will fall within 2 standard deviations from the mean. What that means is if I start at the center of the graph, which would be at x bar, and I move out to the left of 2 standard deviations or 2 s's, and I move to the right by 2 s's, that in between these two values, we should get about 95% of the data. Further, if I move 3 standard deviations, so from x bar minus 3s to x bar plus 3s, I will get about all the data, so about 100%. So if by knowing these couple facts, we can try to estimate, if we have a picture, what our standard deviation might be from a graph as well as our mean. So here is a bell-shaped plot from earlier, and it's hard to read at the bottom, the original scale, so I wrote down 50, 55, 60, 65, 70. So our best guess here is the mean is at the middle here, 60. And then what we'd want to look at is how far do we need to move to the left and to the right to get about 95% of the data. And so if you think about capturing most of this data, but not all, probably about here and here is where we're going to get about 95% of the data in that middle chunk. What we know then is that distance we've moved to the left and the right, that is an increment of 2 standard deviations or 2 s's. Notice I've moved 5 to the left and 5 to the right. So 5 would be 2 standard deviations, meaning the standard deviation here is approximately 2.5. Beyond a graph, if we had the information of mean and standard deviation, we would know then looking at a graph where most our data would fall. So this example is looking at percent of weight made up of body fat for 100 men. We've got a mean of 18.6, standard deviation of 8. We know it's symmetric and bell-shaped because this rule up here is only for symmetric and bell-shaped distributions. We want to find an interval that's likely to contain approximately 95% of the data. So as I mentioned up here above, that interval between x bar minus 2 standard deviations and x bar plus 2 standard deviations should capture 95% more or less of the data. So if we plug in the x bar of 18.6 and the s of 8, we get 18.6 plus or minus 16. So between 2.6 and 34.6 should contain the percent of weight made up of body fat for 95% of our distribution of men.